Hi, I am Varun Joshi and welcome to day 41 of our Certified Kubernetes Administrator 2025 course. In today's lesson, we focus on a critical yet often overlooked aspect of Kubernetes, that is pod security. Through hands-on demos, we will reinforce key concepts and show how to apply security best practices using security contexts and Linux capabilities to protect your workloads. So let's see what I have in store for you. Why is pod security a thing? So before we deep dive into pod security, we must first understand why we need pod security to begin with. So Kubernetes lets you run containers easily, but it does not secure them by default. So if you, let's say, spin up a basic pod, it often runs as a root user inside the container, which can be dangerous, and we'll see why it can be dangerous. But we have been creating pods since the beginning and we have not defined any security related parameters anywhere. So what we get is the default design. So if I go to my terminal and let me create a basic pod, so I'll run kubectl run my pod, and then I will add --rm so that this pod will be removed as soon as I exit. I'll add -it to have an integrated terminal. The image that I want to use for this pod is busybox, and then the command that I want to run is sh. I want a shell so that I can show you a few things. I press enter and I will soon be taken in the terminal of this container. So if I run id, it will show me that I have logged in as a user whose UID is 0, and UID 0 is associated with the first user in the Linux operating system, and that first user is root. The GID, that is the group ID, is also 0, and the groups that this user is part of are the root group and the wheel group, and wheel group is also associated with administrative privileges like sudo and su. Now if I run who am I, the output we know is going to be root, because this container is essentially running as root. Some of you might be wondering that if my containers are running as root, then what is the problem with that? Understand, when we talk about security, when we talk about any production grade implementations, the first thing from a security perspective that should come to your mind is principle of least privilege. So whatever permissions you are giving to any user or to your operating system or to anything in general ITs, for your cloud accounts, for your system users and so on, that access should be adhering to principle of least privilege, which says only grant the permissions to perform the things that are needed to be performed by that user. Do not give any extra permissions. So let's go back to our diagrams and understand why running your containers with the root user can be counterproductive for you. First is privilege escalation. If the container is compromised, an attacker could attempt to escalate privileges and break out of the container. So understand, firstly, if my application is running using the root user and some malicious actor compromises my container, in that scenario, firstly, since it is the root user, it can perform any system level configurations. Any root privileges will be available at the disposal of that malicious actor. And not just that, if special permissions are granted, then that container, that user in the container, can also access the underlying host's kernel. So that is dangerous. And second point is the same. access to host resources in less strictly isolated environments, example without user namespaces or pod security standards, a root container may gain elevated access to the host system. And third one is accidental misuse. If my application doesn't want the root user, if my application is not performing any system level configuration changes, my application just wants to simply run, it is not performing any other action, then why do I need to run my application as a root user? Because let's keep aside malicious actors or a virus attack, let's only concentrate on accidental misuse. What if application running as root can unintentionally modify critical files or perform actions that would otherwise be restricted? Hence, it is not recommended to run your applications as root user. Non-compliance. Now, any client or any project that you deal with would want to adhere to certain security standards and also compliance standards. Security, when I talk about an organization, security can be subjective. Security for me can mean something else. Security for you can mean something else. And similarly, for organization A, something is secure, and for organization B, that something is not secure. Hence, security is subjective. But when I talk about compliance standards, these are set by third-party companies. For example, if a third-party company has set a compliance standard, to adhere to that compliance standard, your application or your containers should meet those specific things. So if the compliance standard adhered by your application warrants you to use non-root user to run your application processes, then you must be running your processes with a non-root user. Hence, using a root user can result in non-compliance when you are dealing with certain industries. And if I talk about security in general, we must adhere to principle of least privilege. Hence, an application must be running with a non-root user. And last point is the same. Pods could access hosts, and I will remove this point because this is redundant. Now, in the initial stages of this lecture, I said that whatever pods we have been creating, they are running as root, and we have seen that behavior. We have used Nginx, BusyBox, Ubuntu, and so on, and all of them were running via the root user. And when I say all of them were running as a root user, I want you to understand that the process inside that container was running as a root. For example, if Nginx is running the Nginx web server, that web server was running using the user root, and any files you created or any files you modified in that container will have the ownership of the root user, and that is understood. But why I am mentioning this? Now, not all containers are run as root. Some container images are designed to run as non-root. For example, if I am creating a Docker file and I specifically add a couple of instructions in that Docker file, that would result in the application running in non-root user, and that is possible. So if I scroll to the left, you see I have two Docker files here, and these Docker file, if you see the second instruction here, the run instruction is creating a user, and if you see the second last command is switching to that user, and the command finally is run by that user. So in this example, it is the app user who will be running the process in the machine. So what will happen is this Docker file will result in a container image, and that container image will be associated, let's say will be running a container, and that container the application will be running as the user app user. And similarly, in example 2, we have not specified a username, but what we are saying is I want to run the application, which is signified by CMD. I want to run the application with the user ID 1000. Understand that in Linux operating system, whenever you create a user, that user has an associated user ID and also a group ID. But in this Docker file, I am just mentioning the user ID, but I want you to also understand that usernames are there so that we humans can read them, can understand them. But under the hood, the Linux operating system just cares about the numerical values, that is the user ID and the group ID. So I wanted to bring that distinction right here. Then let's talk about the second point. The second point says security conscious base images. There could be certain distroless or bitnami images that do not run as the user root, but I do not want DevOps engineers or infrastructure engineers to rely on these, because we don't know these for sure until and unless we check the Docker file or we check the container. Hence, I want DevOps engineers and infrastructure engineers to specifically add certain parameters which will ensure that the containers in my environment are running with a non-root user, and also adhere to few other security parameters. And we will see what those security parameters are in a little while. Hence, explicitly define security context fields. And what is security context? We will see that in a little while. Second is enforce policies, and we learned about these in day 38. We learned that you could have admission control in place so that the requests that do not adhere to what you mentioned are not catered. If you have any confusions about admission control, then do watch day 38, because when we talk about pod security or your cluster security as a whole, then admission control is one of the critical concept to understand. Now let's go back to day 41 and see what I have next for you. So in this section, we understood why pod security is a thing. In the next section, we will define how to achieve pod security. Now let's scroll a little down. I will just quickly zoom out a little and then I will zoom in again. So if you see on screen, there is pod security at the very top, and then pod security can be achieved via two things, and I'm only mentioning the two most important things. There are few more concepts as well that are not relevant, at least for now. Hence, I have only mentioned the two most important concepts here when we are dealing with pod security. The first one is security context, and the second one is Linux capabilities. When I talk about security contexts, these are applicable at both container and pod level, but Linux capabilities are only available at container level. So let me zoom in again and let's concentrate on security context for now. I have segregated security context into three categories. Pod level, as in you can only have this security context at a pod level. Pod plus container level, so you can define these at both pod level and container level. But if you have defined it at both pod and container level, then container level will take precedence. Otherwise, when I say pod plus container level, you can either specify them at the pod level, and when you apply this at the pod level, all the containers within that pod will adhere to those security contexts. And if you define at container level, then you can choose which containers should be having these settings. But again, if something is applied at both pod and container level, then container level will take precedence, then last is container level. So these settings can only be defined at container level. So now let's understand first pod plus container level settings, and then I'll come to the pod level. First is a runAsUser, and this is very simple. As the name signifies, a runAsUser, this will instruct the container that whatever process you are running, you must run it with this user. So what you do is you specify the user ID here, and in the demo section we'll cover most of these settings so that you completely understand how these things function in a production grade implementation. Second is runAsGroup. We are specifying whenever this process is started, I want you to run as this GID. Then the last one is run as non-root. So once you add this, then no matter what, your containers will not start with the root user. They must start with a non-root user. For example, if you do not have these two settings and you only have this setting, then you will not be able to run your Nginx container, because we know that by default Nginx container runs as root, and you have added this flag. Hence, this flag will only allow the container to run if your container is running as a non-root user. So if we try to run a container that uses this Docker file, or the container image that uses this Docker file for creation, then that container will successfully run. Let's come down again and let's talk about container level parameters. Now, the first one that I want to discuss is allow privilege escalation. Prevents the container from gaining additional privileges. Varun, in English, please. Suppose there is a binary owned by the root user with the set UID bit set. Now, even if a non-root user runs it, it will execute with root privileges. And why is that? Because we have set the set UID bit. Now imagine your container is running as a non-root user, let's say with user ID 1000. Without protection, okay, if you are not having false for this, then that container could run such a binary and gain root level capabilities inside the container, even though it didn't start that way. Second one I want to discuss is privileged. Gives the container full access to the host, including kernel level operation. So in production implementations, you would typically set this to false. The last one I want to discuss is a read-only root file system. Mounts the container's root file system as read-only, and this is important. If my application is not performing any sort of modifications in the system level configuration files or system files, then why do I have to give permissions to my application to modify something? If my application modifies something, then I should, but if it is not, then I should not. Understand that if an application is just supposed to read some data and it is not modifying something, then it is important you set this to true. And once you do this, anything underneath slash, that is the root directory, will not have your application. Anything under the slash directory, that is the root directory, your container will not be able to create or modify any files, because mounts the container's root file system as read only. But Varun, what if my application wants to modify some data that is, let's say, coming from an external disk? For example, what if I am using host path mtdir, or the recommended way, a pvc? How can my application modify that if you set this to true? And again, I want you to understand that you can always use fsGroup specifies the gid that owns the mounted volume. So if you have specified an fsGroup, for example, then anything that is mounted will have special permissions to modify and write files to that directory or to those directories, those mounted volumes. So if your application, let's say, does not modify any of the system configuration files but needs access to certain mounted volume, then you can set this to true, and then you can also specify this, and we will be seeing these things in the demo today. So now that we have a solid understanding of security context, let's go to the demo section. And before I go there, I also want you to know that you can always visit the GitHub repository, which has properly formatted notes, so that you as learners can, after the video, read these notes to have a solid understanding of all the concepts. And I went a step ahead and also added what are the recommended values, so that you as a participant know what to choose when you are dealing with a production grade implementation. Now let's go first to Visual Studio Code, where I have already created a security context YAML. So I will increase the font size, and then it's a simple pod manifest. We are calling this secure pod, and here is the important part that I want to discuss. I am saying run as user, whose UID is 1000, run as group, whose UID is 3000, the fsGroup is 2000. So if I have mounted anything, mounted a volume, then that volume should have ownership of this fsGroup, so that my application can modify that directory, can create files in that directory, can delete files in that directory in that mounted volume. Run as non-root is also set to true. Then in the containers section, what I am saying is allow privilege escalation is false, read only root file system is true. So my application will not be able to write any file. I want you to understand that right now fsGroup 2000 is of no use, because we are not mounting any volumes onto this container. But in the next demo we'll see that, and then this will make sense. I added this here so that you can understand how this works in conjunction with this setting. And for now we can also comment this, but I'll leave it as is. Now I'll remove this extra hyphen, and then let's run this YAML. So I'll go to my terminal, I will exit this pod, and it will be auto deleted because I added -rm. Then I will run kubectl apply -f. I am already in day 41 and I want to apply the YAML whose name starts with 01. I will write 01, press tab, press enter, and it says secure pod created. Now let's see what I want to do next. So I will kubectl exec-it. I will name the pod, that is secure pod, and I want sh because we are using busybox that has shell. I'll go inside it, and the first command I want to run is mkdir test_dir, and once I press enter, this says can't create directory, read only file system. And why is this? This is because of this setting. This is a read only root file system. Let's now run sudo su. Let's run su hyphen. So in the busybox image, you do not have sudo or su installed by default, but what I want you to understand is, even if you would have this installed, then also these commands won't run, because we have supplied allow privilege escalation as false. Now let's again go back here and let me run who am I. Oh, who am I not. And you see that UID is 1000, and it says unknown here because we did not specify a username. Do not think this as an error. Linux security is based on UIDs and GIDs, like I said before, not usernames. Username is optional and only needed for human readability, but for now we can understand that it is UID 1000 which is running my process. So if I run psaux here, then you would see that sleep 3600, and that is the command that I have run, sleep 3600 in busybox. You see that that is running with user ID 1000, and that is what we expected. If we wouldn't have added these security contexts, we would have seen that this would be running as the root user, and that we understand is a problem. Now let me exit this container. So once I hit exit, I am out now. What I now want you to concentrate on is demo 2. Let's open two security contexts for demo 2. So here what we are doing is we are creating a pod named secure-writable under the spec section. So these are the parameters that we are defining at the pod level itself, security context, and then we have defined, like before, run as user, run as group, fsGroup, run as non-root. All these we have seen before. Here as well we have the same thing, allow privilege escalation false, and these things we are defining at container level. Allow privilege escalation, let me add a dash here so that these lines disappear for a while, and these lines are coming because I have not supplied requests and limits for my containers, or you can also specify them at pod level. So I have not done that, hence you see those lines. So now what we are saying is container is app, name of the container, then image is busybox, command we are running sleep 3600, which is essentially sleep for an hour. Security context, allow privilege escalation is false, read only root file system is true. So I cannot perform any write operations in my root file system. But what I am also saying is this pod has a volume associated with it, and that volume's name is writable volume, and this is of type empty dir, and then we are mounting that volume onto the pod with the volume mounts section. Name is writable volume and mount path is /writable. Anything that we create in root file system or anything that we modify in the root file system will be denied, but this will be allowed because fsGroup specifies the GID that owns mounted volume. So this mounted volume will be owned by GID 2000. Now let's go to the terminal and apply this manifest. So I will run ls, I will then run kubectl apply -f. I want to apply 02, that is for demo 2, and then I will press enter, and this says secure writable created. So what I will now do is I will exec into this pod, kubectl exec -it. I want to enter into secure writable pod, and then what I want there is I want an sh, a shell. So I will run id first, and as expected, as we saw before in the previous demo, the UID is 1000, GID is 3000, and groups are these. And why are these? Because we defined them here itself. If I run ls-lthr, you see that ownership is of root, and we also see a writable here, but this one, this is owned by root, but the GID is 2000. And why is this 2000? Because we defined 2000 here, and what is fsGroup specifies the GID that owns the mounted volume, and here the mounted volume is named Writable because that is what we called it, and then it has ownership of GID 2000, and my user, that is user ID 1000, is part of this group here. Hence, if I try to create something here in this directory, it will work. So first, let's try to create a directory here named testdir like we did before, and this will obviously fail. And if I cd into Writable and then I run this command again, then this will succeed. And if I touch my file, this command will also succeed because my application, which is running as UID 1000, has access to this Writable directory, this volume. And why is that? Because we have specified 2000 as fsGroup, hence the GID 2000 has rights on Writable volume, Writable directory. If I run ls-lthr again, you will see that owner is 1000 and the group owner is 2000, which is the expected behavior. I hope you clearly understand security contexts, and you also understand how powerful they can be in production implementations. So let's exit out of this container. What I want to now do is I want to kubectl delete -f01, and then I also want to perform the same for 02. I'll also delete 02. Now that both the pods are deleted, let's go to our drawings and see what we have next. Now what we want to cover is Linux capabilities. I want you to understand one thing, that root privileges, when I talk about root privileges, we understand that there are plenty of things that come under root privileges, and these plenty of things are distinct low-level permissions called capabilities. Hence, Linux capabilities can be thought of small bifurcations within the root privileges. So for example, if I have a container, I might allow that container to modify the sys time, but I might not allow my container to modify network settings or my Ethernet adapters. Hence, Linux capabilities allow you to do certain root level things and can also deny you to do certain root level things. What I have mentioned here is not a comprehensive list. There are more, but I have only jotted down the important ones. So the first Linux capability I want to discuss is chown. So if you have this at container level and you have set this to add, and we'll see why I'm saying add. So what you can do is, when it comes to Linux capabilities, you can drop them and add them. So if you add this capability, then your containers will be able to change ownership and change ownership using chown for files and directories. Then next is systime. This is there to manage the time sync services, example NTP. So you can use this to change the date and time of your container. Then there is net_admin, net as in network. This allows you to modify network interfaces, routing tables, and firewall rules. So once we do the demo, this will make much more sense. So let's go to the demo straight away. So I am in Visual Studio Code. I will close this file. I will open 03 capability pod.yaml. So we are creating a pod that is called cap-pod. I'll again add a hyphen here so that the lines disappear. I have the spec section. Under spec section, I'm only creating a container. That container's name is app, image is busybox, command is I'm asking it to sleep for 3600 seconds. Then there is security context again. What? Varun, we were discussing security context a while back. So I want you to understand that underneath security context, you define capabilities. There is no separate block right inside the container block that will talk about capabilities. You have capabilities right underneath the security context block. So this, what I am doing is the recommended way. What I am saying is drop all the capabilities for now and only allow my containers to do these things. But if your application, for example, does not want these privileges, then you can entirely remove this section, as in all the capabilities will be dropped by default. But Varun, how do I know this? You know this once you have your container image. You can drop all the capabilities and then ask your application teams to check whether the application is working fine or not. If there is an error, then you ask them what that error is and work with them to add appropriate capabilities in the add section. But always have this capability section, because you do not want your containers to perform actions that are highly privileged. So let's remove this dash. In this example, what I am allowing my container to do is I'm allowing it to add remove network interfaces and then change the system time. So I will go back to my terminal. I will clear my screen. I will run kubectl apply -f. Then this one is 03 capability pod. I'll press enter and this will create the cap pod for me. I will now run kubectl exec -it. Name of the pod is cap pod and I want a shell here. If I run id, this is running as root because we have not defined any of the other parameters in the security context. We have just said allow privilege escalation is set to false. Now let's go back here. What I will now do is first I will run IP link show. This will show me all the adapters, and here what you see, there is a loopback adapter which is in up state. So what I want to do is I want to do IP link set LO, that is the loopback, and I want to down this thing. And as soon as I press enter, it has shut down that loopback port adapter. So if I run this again, you see that loopback is, you don't see an up here. Previously it had an up. So we came to a conclusion that we are able to run this command. So I will again set this to up to change this to the default one. Now I also want to show you that I can, change the date of this. So what I'll do is I'll paste a command here that will change the date, and here is the command. I am changing the date to, so but before I do that, I also want to show you what is the date in this OS right now. The date is set to June 28th. So let me change this date to what we desire. So I'll close this and then I'll press enter, and now if I run date, you see the date has changed. Now this is fine, but I also want to show you that what is something that will not work. So if I go to my diagrams, you see I have chown as well. So what I will now do is I will touch a file named my file, and if I run ls, you see my file exists here. If I run ls-lthr, root will have the ownership for my file, and that is what we expect because we are logged in as the root user. And then what I can now do is I want to change the ownership. Understand that I am logged in as root and I should be able to change the ownership here. So let me run chown 1000 and 1000. I want to change the ownership to this user ID and that group ID. And then I will run simply my file here and I'll press enter, and it says operation is not permitted. And why is this operation not permitted? This is not permitted because what we have defined in our YAML. We have said drop all other capabilities and only allow these. So I want you to clearly understand that this is how these things work. Now I want to show you one more thing quickly. I want to re-engineer this. I will comment this and let's keep drop to all, and once we do this we cannot do any of these things as well. So what I can do here is I can exit this container for now, and then I can run kubectl apply -f. I will apply that file again, but before I do that I'll have to name this pod -2. I'll save this and then I will apply this, and this says it is created. And now what I will do is I will go into this pod, and previously the commands that succeeded, for example if I run date, this is showing the date, but if I now try to run that date command again, that command will error out because I have set that date cannot be changed, because I have dropped that capability, can't set date, operation not permitted. So if I now run date, you see the date is still set to 28th June, and previously when we run that command, date was set to June 1st. So we understand this, and similarly this will work the same way for your IP link command that we used. But another important thing I want you to know is you start with this and then see how your application behaves. If your application is not functioning properly, you check the error logs of the application and then add the needed capabilities, but do not start with add all, never. So I think I've covered whatever I wanted to cover. That concludes today's lecture. What we covered is foundational for running secure production grade clusters, especially in multi-tenant environments or where compliance is critical. As for day 42, I haven't finalized the topic yet, so stay tuned. It is going to be a surprise. If you have any questions, feel free to ask them in the comment section and I will reply. If this helped, do consider liking, sharing and subscribing. It will mean a lot to me. Thank you very much.